So the site that we're going to work on today is just an example site where we might dig a pit. You'll be given predetermined locations for pits that are based on the science questions being asked. They may be randomly located in some kind of algorithm for the science, but they'll probably be marked with a stake or a pole or a PVC rod, something like that. If they aren't, you'll be given GPS coordinates to find them. Either way, you'll probably use a GPS to get close to the site, and if you don't have a marked site, then you use a GPS to get right on the site. Don't spend a lot of time picking the exact site with the GPS. The GPS satellites will be floating, and you'll do circles for hours if you try and stay on the site, and it'll be varying by a few meters all the time. So get as close as you can within a reasonable period of time, a few minutes, and then pick your site and dig your pit. Don't spend a lot of time tromping around ruining the site either, trying to get exactly on it. Get close, as close as you can, and then pick the site, and don't trample the site because you'll alter the snowpack that you're trying to measure. You will use the GPS to record the coordinates from the GPS in your data book to show the actual site you used, and you'll be given a handheld GPS for that purpose. When you get to the site, take out your probes. You'll be given 1 meter probe sections, and I'll show you how to assemble those. It's not tricky, but I'll give you a little demo on that as well. Assemble these probes and probe the area just a little bit to make sure you're not on top of a boulder, a buried VW bus or something that'll cause problems once you start digging. If there's a little bit of roughness at the bottom, that's typical, and there's no point in moving your site around to get rid of a little bit of surface roughness underneath the snowpack. You just don't want something like a tree or something that's going to compromise your pit measurements. Also, don't probe around looking for a shallow spot if you're tired of digging, or a deep spot if you're trying to get the deepest pit of the day on your crew. Pick the site based on the coordinates you're given, and that way you won't bias your sample. Probe a couple times, leave your probe in the site while you get your other tools out. Mark the site with the probe, draw a line on your pit face that you're going to leave undisturbed, and the area that you're not going to throw any snow in, and then start your excavation. If you're working with 2 people, which you're more than likely to be doing in a team, one person can start filling out the data header, the date, time, location, GPS, all that stuff, weather, while the other person starts to dig. If you happen to be working by yourself, you can fill out some of that data, then dig your pit and fill out the rest of the data. And we'll go through all that protocol now. All right, I've grabbed my 2 probe sections. In some cases you'll need 3. That means you're in a pretty deep snowpack. Hopefully you won't have too many of those. Each probe has 2 set screws. They face opposite sides. You set the probe by taking a screwdriver and screwing those in so that the little nubbin goes out the other side just flush with the surface. Don't go too far or you'll strip the aluminum right out. Do both of those and you're good to go for depth. You can use an avalanche probe for this quick part if you're carrying one of those. Something like this works really well. One of these extendable avalanche probes. And it basically does the same thing. Either one of those will work. You'll be carrying these 1 meter probes with you anyway, so you don't need the avalanche probe. Okay, I'm gonna probe and look for things underneath the snowpack that'll mess up my pit. Oh, I got some deep snow here. That feels like a log. It's making a different sound. Feels pretty soft in here too. Yeah, I'm in some mud on the bottom here. All right, I'm not feeling anything too strange. I'm noting my depth so I know roughly how big to make my pit. I'm almost 2 meters here. If I make too small a pit, it's hard to throw the snow out when it's deep like this. So I'm gonna make a pit that's about 2 meters by 2 meters here, and that'll give me lots of room to work when I'm digging the snow pit out and then when I'm sampling it. Once I pick my spot, which I have here, I'm gonna make a couple of marks, and these will be parts that I won't disturb because I'll be doing sampling on these two faces. So I've got two walls here that are gonna stay clean. I'm gonna dig everything in this corner out and throw it this direction. I'll leave this probe in here and I'll start digging. Okay, I'm gonna dig this pit a little bit bigger than I normally would just so that we can shoot the video. But the important thing is to dig it big enough that you can get the snow out easily. I'm gonna put my shovel together, extend the handle so I can get more snow out faster. And I'm gonna orient my pit. The reason I chose these lines is the sun is behind the pit wall here, so I won't compromise this pit through sun directly on the face that I'm trying to measure. It will help me with temperatures, for snowpack temperatures, and it will help me with the crystal ID and stratigraphy in terms of not heating up the pack. So I want two walls that'll stay shady. I've got the sun pretty much to the south here, so I have a north-facing wall, so that works well in this hemisphere. I'm gonna dig this out. These shovels will last a long time if you don't pry with them. If you stick them in the snow and lever like this, you'll go through this shovel in a matter of a couple days or a single pit. This particular shovel is 20 years old and it's doing quite well. The key is in harder snow to carve out chunks. This is nice soft snow, I can just dig this out, but when we get to lower layers in the snowpack, I may need to cut blocks. And if you cut blocks, these shovels will last forever. You'll be given shovels like this for the work, so please treat those well. I find it works best to kind of dig out row by row and column by column and keep moving that way. Switch sides so you don't get tired. We got a nice soft layer on top here. I can already feel with my boots that I got a harder layer right underneath it. It's a little bit older, a little bit more well bonded and metamorphosed. So I can tell by the sound of the snow and the feel of my shovel and the feel under my feet that I'm standing on a little bit more well developed layer strength-wise, and I'm about to hit depth hoar again, or faceted snow, and I'll probably disappear. So I'm trying to get as much of this solid layer out as possible before I disappear. And normally with a second person here helping me, they'd be filling out the header information and all the metadata that they can in the pit book, in the data sheets. And they'd also be putting tools that need to stay cold into the snowpack to cool them off. Since I'm working myself, I'll do that after I get the pit dug. So in spite of my best efforts with a probe, I managed to dig my pit right on a log. Hopefully this won't happen to you much, but all your snow pit sites won't be vetted for logs, and in fact, trees may fall down on some of the sites after we pick them and visit them and mark them. So you may deal with this. So what I'll do is just try and move a little bit farther this direction and get rid of that problem. Okay, I've dug the basic pit here, and I'm going to clean up the pit now. Dressing the pit after you've done the basic excavation is a super important part. It allows you to make good measurements, and some of the tools we use depend on a nice flat wall to get a good density measurement. We measure density because the product of density and depth together gives you snow-water equivalence. And ultimately, the most important thing that we're measuring here in the snowpack is the water content of the pack, or the snow water equivalence. And snow water equivalence is the amount of water that you'd have if you instantaneously melted a column of snow. It's a depth, the water equivalence, expressed in a depth. And that's given instantaneous melting with no other losses to sublimation or anything else. So the important thing is to get a flat wall and a wall that's vertical, that doesn't have an apron effect. A lot of times shaving horizontally works really well, especially if you have layers in there that are weak and strong and weak and strong. If you go vertically, you'll often knock the weak snow out with a stronger layer. This whole snowpack is pretty weak, so I can go either direction I want. I want to get right down to the ground. If you got a dirty bottom of the pit, and it's a site that's going to be used multiple times in one winter, try not to throw that dark stuff, dirt and organic matter and whatnot, out of the pit on the surface of the snow, because it'll cause that place to melt sooner than the rest. And if somebody comes back in 2 weeks or a month and digs another pit, it may have altered the site. So keep the dirty stuff in the bottom of the pit if you can. And when you're done with the pit and you're backfilling it, throw that dirty stuff in the bottom first. Just take a minute to get this nice and smooth. It doesn't have to be perfect, but it needs to be flat. So I want to get my instruments that are going to be in the snowpack in the pack so that they cool off. So I'm going to put these density samplers in the snowpack to start cooling off. Otherwise they'll ice up when I stick them in the cold snow. So I'm going to put them over here in the shade. I may not use both of them, but I'm going to have them ready and cooling off. The other thing I want to get in the shade as soon as possible is a thermometer to get accurate temperatures with it. Dial stem thermometer, put that in the snowpack. Other tools, and crystal card also in the snow, because that'll melt the snow faster than just about anything else. Okay, I'm going to close that back up, and I'm going to prep my pit a little bit more. I'm going to make a place to measure density. This technique works really well in deep pits because it gives you a place to work, and it works really well when it's snowing. If you got snow blowing all over the place, it keeps your scale a little bit drier, and it keeps your equipment out of the way from snowfall. The case for the scale makes a good base for it all by itself. We use a folding rule to do depths in the snowpack. It works well to just take your top of your folding rule and put it right in the snow like that. If you have snow that's deeper than 2 meters, which is the depth of that folding rule, you can use your probe section in the same fashion and add another section to it and put it against the wall. Since I'm working alone, I'm going to fill in some of the metadata here. Your data book will have instructions start to finish on the first page. It'll have some, or one of the pages in there, depending on how it's arranged. It'll have item by item details for the metadata, and then it'll actually have a data sheet for measuring the various properties and where you'll record them, and a metadata sheet for the site. So I'm going to fill out the location, my name as a surveyor, the site name will be given to you. You'll fill that in, and the time using 24-hour time for local standard time, a pit number and a date and a time. There'll be some other information here. Weather, you'll do a basic weather summary, windy, gusty, snowing, hard snow, light snow, whatnot. There's a precipitation column. You'll just circle the right answer. Sky cover, wind, ground condition, ground roughness, ground vegetation, height of ground vegetation, and the canopy. If you're in a treed site like this, if you're not in an open site. Even in an open site, you'll record that. On the data sheet itself, you'll record the same information, some of the same information. You'll do location, surveyor's site, pit ID, and that kind of stuff. And the reason that we do that redundantly on both sheets is that if the data sheets get separated, we'll know which goes with which data sheet. So which metadata goes with which data sheet, which is very important. This one also has a total depth and some other actual items related to the site. A slope, an aspect. You'll have a compass that you'll take a bearing. The aspect is the fall line. If you stuck a basketball on the surface of the snow and it would support it, it's the direction that that would roll if you just let go of it. And that's in degrees, and you can just ballpark that within 10 degrees from your compass. Slope, you'll use this compass or a slope meter to get the slope, and again, you can get that fairly close. So we're not too concerned with that. We can always get that information off a digital elevation model from the location. You will record your UTMs in here, easting and northing, as well as the UTM zone. And again, there's a comment section here for notes. The first thing we typically do is temperature, because temperature changes so quickly as soon as you open up the pit. You want to get your thermometers in there and start that protocol right away. We have 2 thermometers in each snow pit. We don't want you to use both of them. One's a spare in case you step on one or lose one, or one stops functioning for some reason. If you use 2 and they aren't perfectly calibrated together, you'll get a leapfrog as you go down the pit that'll show a unrealistic change with each depth. We're more interested in the relative change than we are the absolute accuracy. So using one thermometer gives you a relative change between the layers, which is what we're after. So even though you're tempted to use two thermometers to be speedy, don't do that. You can be plenty fast just using one thermometer. Our total depth here is 169 centimeters. We take the surface temperature, and then we do a temperature every 10 centimeters all the way to the base of the snowpack. So in this case, since it's 169 centimeters is our total depth, or our HS, we would do a surface measurement at 169, then we'd go to 160, 150, 140, ad nauseum to the bottom of the snowpack. Now that's a little bit slow because you want to let your thermometer equilibrate at each level. You don't want to move it too fast or you'll get an anomalous measurement for that layer. So the best thing to do is to do your temperature measurements along with another activity, and another one that you want to do as quickly as possible in the snowpack is your stratigraphy, your grain size, grain type, and layers, because that'll also change on a hot day or even on a mild day as soon as you open up the snow pit. So I'm going to start going through some of that stuff. I will have filled out my header information here already, and I'm going to start some of these measurements. So I've got my thermometer in the snowpack on a shaded side, and I cooled it off. When we do surface temperature, we have to shade it from the sun or we'll get a bogus measurement in terms of temperature. And the standard protocol is to stick the shovel in with the blade off the ground so that it's shading the site that you're going to make the measurement, and stick the top right in the shade right on the surface and wait for that to equilibrate. I'll give that a couple of minutes sitting there. You want to put your shovel in a place that's going to shade the top 30 centimeters of your measurements too, because you will get penetration of shortwave radiation that will heat up the thermometer in the snowpack, and you'll get too high a temperature if you don't shade it. So pick your shovel location closely. You'll notice I didn't jam the shovel in all the way because I want airflow through here too. But it's just the shade that's important. It's hard to see the shade at this point because I got a little bit of tree shade here too, but I can see that the tip of my thermometer is in a shadowed area from the shovel itself as well as the tree. My thermometer stopped moving and it's saying -10. degrees C. So I'd write that in my book at the 169 level. And then I'm going to move it to 160, and I'm going to make sure that's still in a shaded spot. I'm going to insert it horizontally there, and I'm going to let that wait. In the meantime, I'm going to start my stratigraphy, and I'm going to put on a glove to do that. Most of these measurements should be done with gloves on so that the heat of your hands doesn't mess things up. And I'm just going to start by checking. This is a hand hardness test. It's a standard test used in the avalanche world, and it gives you some indication of the strength of the snow through hardness. Hardness is the thing we measure, and it's a surrogate variable for strength, which is also a surrogate variable for the state of the pack in terms of strength and metamorphism. We got really soft stuff up here. That's probably relatively new snow. I'll look at it through a glass here in a second. But you want to push just hard enough that if you push on your nose, it's a little bit uncomfortable. It hurts a little bit. That's about the right pressure. You can look in the literature for actually a kilogram force or a Newton force or a pound force for that measurement. So I'd call this fist up here, and then right about in here, it turns into something I would call forefinger. So I got fist, it's really forefinger here, one finger in here, and I go back to fist. There's a little bit of a layer right in here, and I go basically fist all the way to the ground. So I'm going to put some markers in here. I'm going to do this over closer to my tape so that I can record where they are. There's something right there. Another technique for looking at this. Something right there. It's weak again there, maybe. A layer there. And there. All the way to the ground, but there's another super weak layer at the bottom. Another thing you can do is take a paintbrush and scrub this a little bit, and it'll make layers pop out that are easier to see. Be careful. If you brush in the same spot over and over, you'll create a layer difference that may or may not be real. This may just be a slight change in the wind during a storm, or a pause in the precipitation between the storm. So I'm not seeing much in here that I'd call real layer difference, and my hand hardness didn't pop it out either. But this is, I'm going to adjust these a little bit with new information. Maybe take that one out. And we don't want every little micro layer in the snowpack. We want to get the basic big differences. So I'm pretty comfortable with that now. You can see there's a little bit of variation in there too, but I'm not going to record that. Okay, I should be taking temperatures. My temperature at 160 is minus 12 degrees C. You can see that surface is heating up a little bit. We've got colder temperatures underneath the surface. I'm going to use my crystal card, and I'm going to look at these different crystal types as I go down. I'm watching that thermometer equilibrate. It's still moving a little bit. Gonna look right on the surface and see what I got here. Have a little bit of surface hoar right on top. And we're gonna do grain sizes. We do a very rough grain size approximation. We look at 3 different classes. We look at smaller than 1 millimeter, 1 to 5 millimeters, and greater than 5 millimeters. You'd be doing this differently if it was for a different purpose, but for remote sensing, that's in this project, that's what we're going with. So I'm gonna call those surface hoar, and I'm gonna write that in the grain type, and I'm gonna call it less than 1 millimeter. Next layer down, I'm going to characterize this whole layer from stratigraphy standpoint. So what I'm going to do is go in my book and write down my layers. And we write down the top and bottom layer for each layer. So the first one's going to be 169. My next layer boundary is at 135. So I'll write 169 to 135. My next one will be 135 to 118. Next one is 118 to 103, then 103 to 85, and 85 to 17, and then 17 to 0. So I'll write those in there. I'll put in my grain size for each, my grain type, and I'll put in my hand hardness. So we're interested in what's right at the surface. So in my first layer here, I would write down just surface at 169 with no depth, really. And if it was a great big surface hoar, a centimeter thick or something, I'd write 169 to 168, but it's just the nearest surface layer. So I'm just gonna write 169 and a dash for the second depth for the thickness. And I'm gonna call it surface hoar. It's less than a millimeter, and it's gonna be hand hardness of a fist. The next layer will be, again, 169, kind of at the surface, to 135, and it's fist. I already did the hardness measurement. Now I'm gonna take a look at that in terms of the actual grain type and also the grain size. I keep cooling off my card just by sticking it in some cold snow here, and I'm probably ready to take another temperature measurement. You can read these dial stems, these big dial stems, to the nearest half a degree, and I got minus 12.5 at 150, and I'm going to move it to 140. And then I'm going to look at this next grain type. I'm going to carefully tap that surface to spread them out. And I'm going to look at these. Okay, this is new snow that's decomposing and faceting. So I'll probably, in this case, write down, for a grain type, I'll put fragments of new snow, and I'll put arrow pointing it towards faceting. You can use either a symbol or the letter code given in the metadata sheet. For these crystal types, it's better if you use the letter code because we can machine learn a data collection algorithm to translate that data into something useful, and it won't do that so well with the symbols. So letter codes are preferred. If you're used to the symbols, you can use those as well. This grain size is, again, less than a millimeter. I'm going to look at another size here, though, lower in that layer, and just make sure it's consistent. It's pretty much the same thing, faceting new snow. Okay, another thing about grain size, this is something that's really hard to do, and people struggle with this. We're looking for the average grain size, the average large grain in there. So not the smallest. We're kind of interested in don't pick out the biggest grain you see. Pick out the sort of average large grain in there, and that's very subjective. There's 2 ways you can do the grain size. These crystal cards have a 2-meter grid on them, so you can look at the grains on there. You need to spread them out enough that you can see the grid on there. And it's a 2-millimeter grid, so you always know what size it is. These are definitely 1 millimeter and less on average. These macroscopes also have a graduated reticule in them, and if you turn the top knob, that'll come into focus. The top bar on that is millimeters, 5 millimeters across, and it has tenths of millimeters, so you can be quite accurate with that. You can do either one. Okay, so I'm going to call that one fragmented new snow or new snow fragments turning into facets. Okay, I'm going to give you another temperature, minus 11 at 140, and I'm going to go to 130. So I'm just stepping down my thermometers and stepping down the stratigraphy at the same time. Next layer, I called 4-finger in here. So I'd record that in my book, look at the grain type. Now I have kind of a mixed layer. I have facets that are fairly well bonded. The grain size is bigger now, but it's still less than a millimeter. But now what I see is facets that have undergone some rounding. So I would write my letter code of facets with an arrow pointing at rounding, and that's why they've picked up some strength. They're starting to bond, and I could just do F with an arrow to the, or a faceted symbol to the arrow, or arrow to the rounding, or a slash in between. Okay, I'm going to do that all the way down to the bottom. As I leapfrog this temperature down, I'm back up to minus 10 at 130, and I'm going to go to 120. Same thing going down. And I'm just going to keep stepping that down while I do my stratigraphy all the way to the base. Again, you're going to pick out major layers here. We're not interested in every micro level. You could pick out 100 layers in this snowpack just based on slight variation. We're interested in the macro differences, things that the remote sensing tools will actually see from space or from aircraft, things that cause changes in the remote sensing. We're not interested in weak layers. It's not an avalanche snow pit, okay, a stability or instability snow pit. So it's really big differences in the crystal shape and size that we're interested in. And strength is a good indicator of that, so that's why we do that. We don't actually care about the strength of this snowpack for our purposes. When you get to the ground, be very careful when you slide this thermometer in. These things are delicate. They look robust because they're stainless steel. If you tweak this thing at all, you'll change the calibration and it won't be good for the rest of your day or the rest of your pit until you calibrate it again. If you bend it too much, you'll destroy it. So be very careful putting it in horizontally at the base. You're just trying to get this part here, just this tip next to the ground, so you can come in a little bit of angle until you feel this hitting the ground, and then leave it for your measurement. As soon as you're through with that measurement, put this thing away. Lots of times people forget that. They're done with temperature, they leave this in the bottom of the snow pit and they step on it or backfill the pit and forget it, and they don't realize they don't have it until they get to their next pit site and this is gone. It's very hard to find after you've buried it in the snow pit. So last measurement, this goes back in the kit right away and you're done with temperatures. Try and keep the macroscopes dry and snow free. When you take this kit home at night, someone will collect it from you and they'll put it away and dry it out. But they will fog up and ice up and eventually mold inside the lenses, so you got to take good care of that. There is a whole column for notes in the stratigraphy here. You can see if you look really carefully here, there's a layer that has some pine needles and maybe some dust in it. Those are the kind of things that are useful to put in there. If you have some oddity in the snowpack that you want to talk about in terms of stratigraphy or something that might cause a change in the remote sensing signal, this is what we're interested in getting, like a really thin ice lens, something like that. Please record that as well. Anything strange that wouldn't be picked up in your other notes.